Sketching simplified rational functions checklist. So in further maths, you're going to have to sketch rational functions, simplified or unsimplified. For the simplified ones, so far here's a list of points that we can go through to get more information about what it is we're going to sketch. So first of all, are there x or y intercepts? Does the curve have vertical, horizontal, or oblique asymptotes? Does the curve intersect any of its asymptotes? How does the curve behave as it approaches its asymptotes? Does the curve have any local maximums or minimums or points of inflection? And what is the range of the function? And I guess for our context, the how does the curve behave as it approaches its asymptotes thing is more like, does it approach it from, so if this is the asymptote, is the curve kind of doing this? Does it approach it, or does it approach it from below, or what? How does it get closer to the asymptote is really what that's saying. And if you're not really sure, I mean, you can always just plot some points and see if they're above or below the asymptote. For sketching non-simplified rational functions, there's kind of an interesting point. If r of x is a non-simplified rational function, then that means that r of x is equal to p of x times s of x divided by q of x times s of x. And so it's the same as p of x divided by q of x for all of the values of x where s of x doesn't equal 0. So that means the graph of r of x is the same as the graph of p of x divided by q of x, except it has holes. So holes look like this. It's the same for everything, except at that point there's a hole, just to show that the function has no value at that point. So there are holes at all of the points x1, p of x1 divided by q of x1, such that s of x1 is equal to 0. Because if s of x1 equals 0, then at that value of x you would have 0 divided by 0, which is undefined. And of course, q of x1 should not equal 0. So in summary, for non-simplified rational functions, the graph is the same as the simplified version, except at the values of x where the common factor is equal to 0. Then it just has a hole at those points. So here's a nice example of that. We have the function y equals x squared plus 4 divided by x minus 3. This one is simplified. And we see that this is what its graph looks like. Meanwhile, if we consider the function y equals x squared plus 4 times x minus 2 divided by x plus 3 times x minus 2, then obviously we could simplify it by cancelling the x minus 2 out. But leaving it as it is, we can clearly see that y of 2 is 0 divided by 0, which is undefined. But for all other values of x, it's exactly the same. If x does not equal 2, we can just cancel it out. And so if x does not equal 2, then the graph is exactly the same as it is for the simplified case. But if x does equal 2, we cannot get a value there. So it has a hole because it's undefined at that point. Alright, and let's go ahead and do exercise 2.3 now, and we'll sketch a couple of these things. So let's take care of the first one. Sketch the graph of y equals 3x minus 2 divided by x minus 1. The degree of the polynomial on top is the same as the degree on the bottom, so it's going to have horizontal asymptote. Hors s is y equals 3, so 3 divided by 1, and the vertical asymptote is clearly going to be x equals 1, and then well, I guess we can find y and x intercepts. So for the y intercept, x equals 0, y-intercept x equals 0, which would give us negative 2 over negative 1, which is 2. So 2. And then for x-intercept, we would have y equals 0, so 3x minus 2 equals 0. And so the x-intercept is going to be when x is equal to 2 over 3. And I guess we can go ahead and calculate the range of this thing just by finding what values of x are going to give us a value of y. So just by rearranging this equation, we get xy minus y equals 3x minus 2. And so xy minus 3x equals y minus 2. And then we can factor out the x, and we get that x is equal to y minus 2 divided by y minus 3, which is clearly defined for all y except y equals 3. Just to put this into notation that we're familiar with from earlier, if we call this r of x, then this tells us that r inverse of x is equal to x minus 2 divided by x minus 3. Anyway, the main point is that except for y equals 3, for every other value of y, we can get an x that is sent to it. We're assuming that we have the natural domain here of the function r of x. So that's all real numbers x except for x equal to 1. So for every value of y, we can get an x that is sent to it, since this is equivalent to this, which is equivalent to this. So the range of the function is all real numbers y, but y does not equal 3. And lastly, before we sketch it, let's quickly prove that functions of the form y equals ax plus b divided by x plus d, they can never intersect their horizontal asymptote, because if they did, it would be equal to a, and then we would have ax plus b equals ax plus ad, and then we would have b equals ad, which would mean that ax plus b divided by x plus d equals ax plus ad divided by x plus d, which is equal to a. So it wouldn't be a simplified rational function in that case, and in fact it would just be the line y equals a. And clearly it can't intersect its vertical asymptote either. I guess one more thing we can do is check whether it has a maximum or a minimum, so we can differentiate it. So y prime is equal to 3 times x minus 1 minus, and then the one on the bottom differentiates to 1, so just minus 3x minus 2 divided by x minus 1 squared, and that is just equal to negative 3 minus negative 2, so negative 1 divided by x minus 1 squared, which doesn't equal 0 for any value of x. So there are no maximums or minimums. No max or min. Okay, let's go ahead and sketch this thing now. These are x-axes, or y-axes. Now when we're sketching it, we just have to really mark out the key points. I mean, you can be as detailed as you like otherwise, but when you get marked on it, they're just going to be checking that you got the key points right. So first of all, we know there's an x-intercept at 2/3. First, let's mark out. Let's do the vertical asymptote first. So x equals 1 can be here. So this is our vertical asymptote at x equals 1. So you should always include asymptotes as dotted lines on your diagram. And we know there's going to be a horizontal asymptote of y equals 3. Okay, we know the y-intercept is 2, so our function is going to go through that point. And we know the x-intercept is 2/3, so it's about there. We know there's no maximums, no minimums, and that the function doesn't intercept either of its asymptotes. And, well, based on the properties of the function, we know it gets closer towards the horizontal asymptote, y equals 3. And since it doesn't intercept, that means it's trapped below the asymptote the whole time. And since there are no maximums or minimums, it can't like turn around or anything, so it can't be going up and then come back down again. Otherwise there would be a local maximum around there. So yeah, it forces the curve to behave like this. So it gets closer and closer to that line as it goes along. It cuts here and here. Whoops. I missed my intercept. That still's terrible. Alright, come on, hit the mark, hit the mark, hit the mark. Yes, okay. Alright, well, that'll have to do. Try not to be as wobbly as me. In fact, I think I'm still gonna fix this up. It's very hard to draw them freehand, actually. Especially on computer. There we go. So just show it getting closer and closer to the asymptote. And then, oh yeah, you should also mark out the x-intercept is 2/3. And then for the other thing, clearly if x is bigger than 1, we're going to be heading towards negative infinity as x we're going to be heading towards positive infinity as x approaches 1 from the right hand side. So that means that our curve is going to look like this. Now it can't do anything like that because there's no maximums or minimums, local maximums or local minimums rather, and it doesn't intercept its asymptotes, so that forces the curve to look like this. And it just gets closer and closer to that line. Now, I guess I should make this clear.